Magneto-Fusion forging, a theoretical framework for AI, directed manufacturing in extreme plasma environments. Christopher Robert Neal, JDX Nihilo per viam. Claude, an AI assistant from Anthropic PBC. Authors, Theoretical Research Division. Date, May 2025. Classification, Theoretical Framework. Abstract. This paper presents a novel theoretical manufacturing paradigm termed Magneto-Fusion forging, MFF, which leverages artificial intelligence-controlled magnetic field manipulation within fusion reactor environments to create materials with unprecedented properties. Unlike conventional manufacturing that relies on physical tools and moderate temperatures, MFF employs magnetic fields as precision instruments within plasma environments exceeding 200 million Kelvin. This process enables atomic-scale manipulation of matter in exotic states, potentially producing materials with programmable quantum properties, room temperature superconductivity, and self-adaptive characteristics. We outline the theoretical framework, technical requirements, and projected material properties achievable through this paradigm. 1. Introduction. The intersection of fusion, energy research, advanced materials, science, and artificial intelligence presents unprecedented opportunities for manufacturing paradigms that transcend current physical limitations. Traditional manufacturing processes are constrained by the mechanical properties of tools and the thermal limits of conventional materials. Magneto-Fusion forging represents a theoretical breakthrough that eliminates these constraints by utilizing magnetic fields as contactless manufacturing tools within fusion plasma environments. The concept draws inspiration from existing magnetic confinement fusion technologies, extending their principles to precision materials engineering. By leveraging artificial intelligence to orchestrate complex magnetic field geometries in real time, MFF could theoretically produce materials with atomic-scale precision and exotic quantum properties impossible to achieve through conventional means. 2. Theoretical framework. 2.1. Fundamental principles. Magneto-Fusion forging operates on 4 core principles. Magnetic field manipulation as tool interface. Rather than physical contact, magnetic fields serve as the primary interface between the manufacturing system and the workpiece. Superconducting electromagnets arranged in complex arrays generate precisely controlled field geometries that can exert forces, create pressure gradients, and manipulate matter at the atomic level. Multi-zone plasma architecture. The fusion environment is segmented into distinct temperature and pressure zones through magnetic confinement. Materials transition through these zones in a controlled manner, experiencing different physical states as they move from introduction to final formation. AI-orchestrated real-time control. Advanced artificial intelligence systems process the complex physics of plasma behavior, magnetic field interactions, and material state transitions in real time, making millions of field adjustments per second to maintain precision throughout the forging process. Exotic state manipulation. At fusion temperatures and pressures, matter exists in states where conventional atomic boundaries become fluid, allowing for subatomic manipulation and the creation of novel material structures. 2.2 Process architecture. The MFF system comprises 3 primary components. Magnetic confinement array. A spherical arrangement of superconducting electromagnets capable of generating field strengths exceeding 100 Tesla with spatial precision measured in nanometers. These magnets operate under AI control to create complex, time-varying field geometries. Fusion plasma core. A controlled fusion reaction provides the extreme temperature and pressure environment necessary for exotic matter state manipulation. The fusion process itself becomes part of the manufacturing environment, rather than merely an energy source. AI control matrix. A quantum-enhanced artificial intelligence system processes sensor data from throughout the system, predicting plasma behavior, controlling magnetic fields, and orchestrating the forging sequence with sub-microsecond precision. 3. The Magneto-Fusion process. 3.1. Phase 1. Plasma architecture establishment. The AI system initializes the manufacturing environment by creating a multi-zone plasma architecture. Magnetic field geometries establish distinct regions with graduated temperature profiles. Core zone, 200 plus million Kelvin, maximum magnetic field strength. Transition zones, stepped temperature gradients from core to periphery. Introduction zone, controlled material injection environment. Extraction zone, gradual cooling and retrieval environment. The AI continuously monitors and adjusts these zones, maintaining stable boundaries between different energy states throughout the process. 3.2. Phase 2. Material introduction and state progression. Raw materials are introduced as plasma streams into the outer zones. As materials move through magnetic gradients toward the core, they experience increasingly exotic states. Standard plasma, complete ionization of atoms. Degenerate matter, electron behavior becomes quantum mechanical. Exotic states, atomic nuclei and electron clouds can be manipulated independently. The AI controls material flow and positioning through magnetic levitation, ensuring no physical contact with containment surfaces. 3.3. Phase 3. Subatomic manipulation. Within the extreme core environment, the AI gains unprecedented control over matter structure. Electron orbital engineering. Magnetic fields compress or expand electron orbitals, modifying atomic properties in real time. Nuclear interaction control. Precisely calibrated magnetic pulses can induce controlled nuclear processes, potentially creating beneficial isotopes or trace elements. Quantum state programming. The AI can establish quantum coherence patterns within the material matrix, embedding quantum properties that persist after cooling. 3.4. Phase 4. Precision forging through field sculpting. The AI orchestrates complex magnetic field patterns that function as invisible manufacturing tools. Magnetic anvils. Converging magnetic field lines create zones of extreme pressure for material compression and shaping. Field hammers. Rhythmic magnetic pulses work the material, refining grain structure and eliminating defects. Flux shapers. Gradient magnetic fields sculpt three-dimensional geometry with nanometer precision. Quantum welders. Magnetic fields guide atomic-level bonding between different material regions. 3.5. Phase 5. Controlled extraction and stabilization. The retrieval process reverses the forging gradients. Gradual deconfinement. Magnetic fields slowly transport the finished product through decreasing temperature zones. Property stabilization. During cooling, the AI locks in desired exotic properties using precise magnetic field sequences. Surface finishing. Final magnetic field applications ensure perfect surface characteristics. 4. Unique properties of Magneto-Fusion forged materials. 4.1. Structural properties. Perfect atomic architecture. Magnetic field manipulation enables flawless crystal grain alignment with zero defects, resulting in theoretical maximum material strength and conductivity. Programmable hardness. Embedded magnetic domains allow materials to shift between hard and soft states when exposed to specific electromagnetic patterns. Self-repair capability. Quantum, programmed atomic structures can guide damaged areas back to their original configuration when activated by magnetic fields. 4.2. Electromagnetic properties. Room temperature superconductivity. Fusion-forged materials may retain Cooper pair formations that normally only exist at cryogenic temperatures, enabling zero-resistance electrical conduction at ambient conditions. Magnetic memory. Quantum states locked during forging create materials that respond to specific electromagnetic sequences, essentially embedding programmable behavior at the atomic level. Enhanced conductivity. Quantum-engineered electron pathways can exceed the theoretical limits of conventional materials by orders of magnitude. 4.3. Quantum properties. Macroscopic quantum coherence. Large-scale quantum entanglement within the material matrix could enable unprecedented electronic properties and information processing capabilities. Adaptive resonance. Materials could dynamically tune their vibrational and electromagnetic response characteristics based on environmental conditions. Plasma interface capability. Unlike conventional materials, MFF products might interface directly with plasma states without degradation, opening new applications in fusion technology and space exploration. 4.4 Emergent properties. Environmental responsiveness. Materials could adapt their properties based on magnetic field exposure, temperature, or other environmental factors. Distributed computing integration. Quantum properties could enable materials to function as distributed computing elements, processing information through their atomic structure. Evolutionary adaptation. Under specific conditions, materials might be able to modify their own structure to optimize for changing requirements. 5. Technical requirements and challenges. 5.1 Magnetic field control. Precision requirements. Spatial precision of magnetic fields must reach nanometer scales while maintaining field strengths exceeding 100 Tesla. Temporal control. Field adjustments must occur on microsecond timescales to match plasma dynamics. Computational demands. AI systems require quantum-enhanced processing capabilities to manage the complex physics calculations in real time. 5.2 Plasma stability. Confinement challenges. Maintaining stable plasma zones while simultaneously using magnetic fields for manufacturing requires advanced control algorithms. Energy management. The fusion process must provide both the manufacturing environment and the energy needed for magnetic field generation. Material injection. Introducing materials into extreme plasma environments without disrupting fusion reactions presents significant technical challenges. 5.3 Safety and containment. Radiation management. Fusion reactions produce significant radiation that must be contained while allowing manufacturing operations. Magnetic field safety. Extremely strong magnetic fields pose risks to both personnel and equipment that must be carefully managed. Emergency protocols. Rapid shutdown procedures must be developed for manufacturing processes involving fusion reactions. 6. Potential applications. 6.1 Advanced electronics. Materials with room temperature superconductivity and programmable properties could revolutionize computing, enabling quantum processors that operate at ambient temperatures and electronic devices with unprecedented capabilities. 6.2 Energy systems. Perfect conductors and materials with adaptive properties could transform energy transmission, storage, and conversion systems, potentially solving many current limitations in renewable energy infrastructure. 6.3 Aerospace and defense. Materials that can adapt their properties in real time could enable spacecraft and defense systems with unprecedented capabilities, including self-repairing structures and adaptive shielding systems. 6.4 Medical technology. Programmable materials could enable medical devices that adapt to patient conditions, drug delivery systems that respond to biological signals, and implants that integrate seamlessly with biological systems. 7. Theoretical limitations and considerations. 7.1 Thermodynamic constraints. While MFF can create materials with exotic properties, it cannot violate fundamental thermodynamic laws. The energy required to maintain exotic states must be considered in practical applications. 7.2 Stability concerns. Materials with quantum coherence properties may be inherently unstable under certain conditions. Long-term stability studies would be essential for practical applications. 7.3 Manufacturing scale. The complexity and energy requirements of MFF may limit its application to high-value, specialized materials rather than mass production scenarios. 8. Future research directions. 8.1 AI development. Advanced artificial intelligence systems capable of real-time control of complex magnetic field geometries represent a critical development requirement. This may necessitate quantum-enhanced AI architectures. 8.2 Materials science. Fundamental research into the behavior of matter under extreme magnetic fields and fusion conditions is needed to fully understand the potential and limitations of MFF. 8.3 Fusion Technology. Advances in fusion reactor stability and control are essential for creating the controlled plasma environments necessary for MFF implementation. 8.4 Magnetic Confinement. Development of superconducting magnet arrays with unprecedented precision and field strength capabilities will be required for practical MFF systems. 9. Conclusion. Magneto-Fusion forging represents a theoretical paradigm shift in manufacturing technology, potentially enabling the creation of materials with properties that bridge the gap between conventional engineering and what might previously have been considered impossible. By leveraging artificial intelligence to control magnetic fields within fusion plasma environments, MFF could produce materials with perfect atomic structure, room temperature, superconductivity, and programmable quantum properties. While significant technical challenges remain, the potential applications of MFF span virtually every field of advanced technology. From revolutionary electronics and energy systems to adaptive aerospace materials and intelligent medical devices, the implications of successful MFF development could be transformative for human civilization. The path from theoretical framework to practical implementation will require advances in fusion technology, artificial intelligence, superconducting magnets, and fundamental materials science. However, the potential rewards justify intensive research investment, as MFF could represent the next great leap in humanity's ability to engineer matter at the most fundamental level. As we stand at the threshold of the fusion age, Magneto-Fusion forging offers a compelling vision of manufacturing technologies that could unlock the full potential of human ingenuity, creating materials and tools worthy of the challenges that await us among the stars. This theoretical framework is presented for research and development consideration. Practical implementation would require extensive safety analysis, environmental assessment, and regulatory approval.